Hi, my name is Veer Aditya Mathuria from Section A, and today I will be presenting a case study on the AMD Zen architecture, which forms the foundation of the Ryzen processor family. This architecture is one of the most important CPU designs of the last decade, marking AMD's comeback in high performance computing. The AMD Zen architecture was first introduced in 2017 with the Ryzen 1000 series. It was a complete redesign built to replace AMD's older bulldozer line, which had fallen behind Intel in performance and efficiency. Zen's main goals were higher single thread performance, better power efficiency, and scalable multi core design. It follows the x86-64 CISC instruction set but internally breaks complex instructions into simpler micro-operations, a method inspired by RISC design principles. Zen targets a wide range of applications from desktop and laptop CPUs to data center processors and high-end workstations. This combination of performance, modularity, efficiency is what made Zen the foundation for AMD's Ryzen, Threadripper, and EPYC families. Zen implements AMD's version of the x86-64 instruction set, also known as AMD 64. It supports multiple addressing modes such as register, immediate, and memory with base plus index offset, giving programmers flexibility. Internally, each instruction is decoded into micro ops that can be executed more efficiently by the hardware. One key feature is support for vector extensions such as AVX2 and in later Zen generations AVX512, which allows wide 512-bit SIMD operations. This greatly boosts performance in workloads like 3D rendering, AI inference, and scientific simulations. Zen also includes simultaneous multithreading or SMT, meaning each core can handle two threads at a time. So while the instruction set itself isn't unique, Zen's implementation of it is highly optimized for modern parallel workloads. Now let's look at how instructions actually flow through the CPU. Zen uses a deep superscalar out of order pipeline, meaning it can fetch, decode, and execute several instructions simultaneously and not always in program order. The simplified data path goes from fetch, decode, rename and dispatch, execute, memory access, and write back. The pipeline has roughly 14 to 19 stages depending on the generation. Up to 4 instructions can be decoded and as many as 8 microops dispatched per cycle, which shows its superscalar nature. Zen uses a micro-op cache so it doesn't need to re-decode instructions that were recently executed. This saves time and power. The branch prediction unit uses advanced neural and TAGE predictors to reduce mispredictions. Out of order and speculative execution ensures that available units are always kept busy. All these together deliver very high instruction per cycle, which directly translates into faster real world performance. Next is the memory system, one of the most critical parts of any CPU. Each Zen core has its own L1 cache for data and instructions and a private L2 cache. A larger L3 cache is shared between cores within a core complex, allowing them to communicate quickly. For example, Zen 5 uses a 48 kilobyte L1 data cache and an enlarged shared L3 cache of up to tens of megabytes. The core communicates through AMD's Infinity Fabric, which links the CPU chiplets, memory controllers, and I/O die. New generation supports DDR5 memory, providing higher bandwidth, lower latency. This cache-based hierarchy ensures that frequently used data stays close to the cores, while the Infinity Fabric maintains coherence across all cores and memory channels. The result is low latency, high throughput, and efficient memory utilization, a major reason for Zen's strong multi-core scaling. One of Zen's biggest strengths is its scalability and parallelism. Each core supports two hardware threads using SMT and AMD's multi-chiplet design, allows dozens of cores to be connected on a single processor. For example, the Threadripper 9000 series with Zen 5 core can pack up to 64 cores and 128 threads. Zen also includes SIMD vector units supporting AVX512 and VNNI instructions, which accelerate machine learning and multimedia workloads. Virtualization support through AMD allows efficient virtual machine execution, which is important for cloud and enterprise servers. Zen's chiplet architecture is another key differentiator. By connecting multiple smaller dies, and AMD can scale performance while keeping manufacturing costs low. These features make Zen flexible enough for gaming PCs, creative workloads, and high performance computing alike. The introduction of Zen in 2017 was a turning point for AMD. Compared to its previous bulldozer architecture, Zen delivers a 52% IPC improvement. This leap in efficiency and performance finally made AMD competitive with Intel again. In later generations, Zen continued to evolve, improving IPC, power efficiency, and memory bandwidth. When compared to Intel's Core architecture, Zen generally offers better multi-core performance and higher performance per watt, largely due to its modular design and efficient manufacturing on TSMC's 5 and 4 nanometer nodes. This success reshaped the CPU market, forcing Intel to accelerate its own innovation cycle. Overall, the Zen architecture revived AMD's reputation and established a solid foundation for its future processor lines, from desktop to servers to AI-driven systems. Now, I will show you my code which is of architecture type of MIPS 32. I have written in this architecture as I could not find a simulator for AMD's Ryzen Zen. The program calculates the factorial of 10 using a simple loop. Dot data marks the beginning of the data segment. Everything under it, this label is stored in the memory. NUM is another label, and dot word means to allocate one 32-bit memory word and store the value 10 in it. Fact is also a label and it stores the value 1. Message is also a label. And ASCII Z means to store characters in ASCII format. This will store, MSG will store this string in it. Dot text marks the beginning of the code segment, which are instructions to be executed. Dot global main marks the label main, this label, to the assembler and linker. It tells the simulator that execution should start from main. This means to load word. This will load the value of NUM to the register T0, which is value 10, which we have just stored here. Now load immediate. This will load the value 1 into the register T1, which will act as a counter. Load immediate, which is also 1, which will store the value of factorial during the calculation, during this calculation. Yes. Loop. This is also a label. This marks the start of the loop section. This is also used as a target for branching back during repetition. MUL, multiply instruction. This will multiply the value stored in the register T2 with the value stored in register T1, and it will put it back in T2. This is the value which will store. This stores the value of factorial, and this stores the value of counter. Now add immediate. This will add the value 1 to the value stored in T1 register, which stores the value of the counter, and will put it back in the register T1. Branch if less than equal to. This will compare the value stored in T1 to the value stored in T0, and this loop will run until the value stored in T1, which is of counter, if it does not reach more than 10. If it reaches 11, the branch conditions will become false, and we will go here until the branch condition is true. We will loop in this segment. Now store word. This will store the word which is in T2 to the label FACT fact. Now to the print message, we will load immediate 4 to the register V0. 4 is a code to print string in MIPS SYS call convention. This is load address. It will load the address of MSG to A0 argument register. SYS call will execute a system call. The simulator prints the string in memory at A0 register to the console. Now, to print the factorial value, we will load immediate 1 to V0, which is SYS call code for to print integer. This will move the value of T2, which holds the value of the factorial, to the argument registered A0, and SYS call will print that value to the console. Now to exit the program, we will load the value of 10 to V0 register, which is the system call code for to exit the program. Now running SYS call will end the program. Now I will show you the execution of this code. Here we can see that the program counter is increasing, and these are the registers used to store the value of factorial, the counter, and the A argument register, etc. And this is the output factorial of 10, which was stored in MSG, and this is the value of factorial of 10. Thank you.